setter for this. Now let's see the other questions. Okay, so we already focus on inclined plane. So now let's focus on the work energy principle, especially the equation that involve work done against friction. So we want to focus on that, work done against friction. So let's try. Okay, we try a question with work done against friction first. Let's see whether I can find any of it. Okay, so can't find any, but just for your information, if let's say, okay, I just put it here. Okay, so extra information. If let's say the inclined plane is not smooth, and then we will have work done against friction. So in that case, our work energy equation will be like this: the increase in kinetic energy plus the increase in GPE plus the work done against friction is equal to the decrease of EPE. So our situation will be like this now. That means, there is a decrease in EPE where the energy is converted to kinetic energy as well as GPE. But because of the friction, the increase of KE is not so much already. Not so much because of the friction. So the presence of work done against friction, right? Okay, the presence of this making the increase of the KE to be smaller. So you should expect the greater speed will be a smaller value. Okay, the greater speed will be a smaller value if there is work done against friction. So that is how we deal with the work done against friction, where you have to use mu r, the frictional force, multiply with the x. Okay, mu r multiply with the x. So that is the case. And for the r, right, mu of course is given. For the r has to be the r that is perpendicular to the inclined plane. Okay, so as you can see, let's say for the same scenario again. So as you can see, the particles is here, and we have done resolution where this is 0.3 g, and this is 0.3 g sine 30, because here is 30 degree. So you want to find r, right? You have to use this weight component, the other weight component that is perpendicular to the plane, so which is 0.3 g cos 30. This value will equal to r because r is acting this way, as you can see in the diagram here, R is acting this way. So the R and the weight component in this direction is equilibrium because in this direction, the particle has no net force. Okay, they are just moving up only. So they are not moving either this way or this way. So that means they are equilibrium. Okay, so because of that, R is equal to 0.3 G cos 30 degree. So if you have work done against friction, so the R you have to find in that way. The X is how much they move. Same like just now, as you can see here, originally 0.2, then the new X is 0.1, so that means it has moved by 0.1 meter. So the X is hence 0.1 meter. Then you can work it out, work out the new frictional force. I mean the new greater speed. You can find out the new greater speed for this case. Okay, let us look at these questions. This is 2019. Okay, so A and B are two fixed points on a vertical axis with A 0.6 meter above B. A particle P of mass 0.3 kg is attached to A by a light inextensible string of length 0.5 meter. The particle P is attached to B by a light elastic string with modulus of elasticity 46 Newton. Okay, then the particle P moves with constant angular speed 8 radian per second in the horizontal circle with center at the midpoint of AB. Okay, so okay, try to imagine something like this. I try to draw out first. So you have A and B on the vertical axis, okay, as you can see there. So A is up here, B is down here. So they are having 0.6 meter separated by 0.6 meter. Okay, then you have a particle P. Particle P mass 0.3. So we have an extensible string of length 0.5, and then inextensible. So 0.5. Then at B you attach it with light elastic string with modulus of elasticity 46. Okay, there are two strings that connect the particles. Okay, there are two strings. One attached to B, another one attached to A. And the particle P moves with constant angular speed 8 radian per second in a horizontal circle. So imagine that. Okay, let's say I run away my 0.6. I put it further a bit. Okay, so further a bit. 0.6 meter is like this. Okay, now the particle P is moving in a horizontal circle where the center of circle is the midpoint. .3 meter, 0.3 meter. So let's say the particle P is here at this moment. and they are moving in circle. Okay, so there are two strings that attach to P. One is connected from A. So this string is in extensible string. So the length is fixed 0.5. The other string is elastic string attached from B to P. So this is elastic string. So this elastic string, they just give us the modulus of elasticity. They don't give us the original length or the natural length. They don't give. And we can easily imagine because the center of circle is midpoint, right? We can easily imagine that this length is also 0.5 meter. Okay, as the triangle above is similar to triangle at the bottom, so we should expect this BP is also 0.5 meter. Okay, we just know the final length. Natural length is unknown. Now part 1. Okay, so I put the omega first. Omega is 8 radian per second. I just keep it here first. How to use, don't know yet lah. So part 1, find the speed of P. The speeds of P. That means the speeds of P. Okay, V lah. We have to find V. They give us angular speed already. So we want to find the V. V equal to R omega. Okay, so we have to find V. We know V equal to R omega. Omega is 8. R is the radius. Radius we don't know yet. But it is not too hard to find the radius, So you look at the black color one in the diagram. R is the radius of the circle. So to find that, it is not too hard, as the information is quite complete in terms of length. 0.3 is the height over here, and 0.5 is the hypotenuse. So you have 0.3. So R, of course, 0.4. So we just show working now. R equal to 0.5 square minus 0.3 square and square root, Pythagoras theorem. So you get 0.4. So we get R. We have omega given as 8. So V equal to R omega. So equal to 3.2 meter per second. Okay. Now calculate the tension in the string BP. BP. So you look at the diagram again. BP is an elastic string. So we need to count the tension. Of course, you have to use the formula already. Okay, and hence find the natural length of this string. Okay, so tension in the string BP, and then find natural length. Okay, so first of all, let's see. It's a 7 marks question, 7 marks. So let's see what formula should we apply here. Okay, so one of the, you look at the picture, one of the concept that we can apply here is something like this. I put in blue color. The spring, or the string, the string that attached to A is in extensible string. So this string, right, of course it has tensions that act this way towards A. So I call this tension A. Okay. So at the meantime, you should expect the string that attached to B has tension B also. Tension B. Okay, so tension B, yeah. So we have tension B over there. And the other thing that we have to know is the particle P is revolving in a horizontal circle. A horizontal circle. If it revolve in horizontal circle, right? What is clear over here is the component of the tension, which is vertical, right? Okay, so imagine you resolve it. You can easily resolve the TA, right, to horizontal component and vertical component. Okay, the vertical component, right? Okay, let's say this one, the vertical component. This is the vertical component, and this vertical component, of course, to find out it's not too hard also lah. So imagine you want to find theta, right? You can easily find the theta, and then that vertical component, of course, is TA sine theta. TA sine theta, and this vertical component should equal to the vertical component of TB. Should equal. Okay. Imagine the angle will be the same also, will be theta also, because the two triangle is just similar. This triangle is similar to this triangle. Yeah, it is similar, and because of that, we should expect the angle is the same. Okay, so and then because of that, we can find TB sine theta, which act downwards. So the two vertical components should equal to each other. So that the vertically there is no net force, and the particle P remain in horizontal. They won't go higher or they won't go lower. Okay, so vertically it should be equal. So because of that, we get one equation. Yeah, we get one equation, and then we need to solve the equation. Okay, let's see first. Let's see whether we can work it out or not. Okay, so let's work it out. We use the concept where the TA sine theta equal to TB sine theta. Okay, so I find theta first. Okay, I find theta first. Theta is very easy to find. We use the length to help. We use sine, let's say. Sine theta is equal to opposite 0.3 over 0.5. So theta we just inverse sine. Inverse sine 3 over 5. 3 over 5. So we will get 36.87 degree. Okay, now we can get TA sine theta already. Okay, so TA sine theta is equal to TB sine theta. Okay, TA sine theta is TB sine theta. So TA sine theta Oh yeah, I just realized one thing is left out. Yeah, one thing is left out. Let's come back to the picture first. Let's come back to the pictures. Okay, so what I mentioned just now, the force that act upwards is equal to the force that act downwards, which is true. But what is left out is there is also another force that act downwards, which has been left out here. So it is the weight of the particle. The weight of the particle is acting downward as well. Okay, so imagine the weight is 0.3 times 10, which is 3 Newton. This is acting downward as well. So we cannot forget about that. Okay, so because of that, when we look at our equation here, the force that act upwards is TA sine theta. The force that act downward is there are two forces, which is TB sine theta plus mg. Okay, now let's substitute. Okay, let's substitute value for this thing. So we have sine theta, TA sine theta. Okay. Let's say I don't care about the theta. I just simplify my sine theta is actually 3 over 5. So my sine theta is 3 over 5 TB. Okay, again sine theta is 3 over 5 plus mg. So I have 3 over 5 TA equal to 3 over 5 TB plus, okay, mg is 3. We just count it just now. It's 3. Okay, so now what to do is let us simplify this equation. Okay, we simplify this equation. We divide by 3 over 5. So we will get TA equal to TB, and 3 divided by 3 over 5, you end up with 3 divided by 3 over 5, you end up with 5. Okay, so we get one equation here. So let's say I call this equation 1. Equation 1. This is the vertical. Okay, the vertical part. Now let's consider the horizontal. For the horizontal, we look at the picture again. Okay, so we can resolve the TA to get the horizontal. That is not too hard. Okay, to get the horizontal, basically it is going to be TA cos theta. Okay, so which is acting this way. Okay, write away the R first. Don't want to care about the R already. Okay, so TA cos theta. So this component is acting in horizontal. So for TB, we have the horizontal component also, which is also TB cos theta. Okay, so we have two forces that act to the center of the circle. So this is the centripetal force that make the particle revolve in circular path. Okay, TA cos theta and TB cos theta, two of these contribute the centripetal force. So now let's write down the working. Okay, in terms of horizontal, so we have TA cos theta plus TB cos theta equal to centripetal force. Since you have omega, so let's use mr omega square, the centripetal force formula. Okay, so we can find out cos theta easily. As in part 1, we already know the R is 0.4. So then the theta, the cos is 0.4 over 0.5. As you can see the triangle, so the radius is 0.4 adjacent, and the hypotenuse is 0.5. So cos theta is hence 0.4 over 0.5. So let's write down first. Okay, we write down at the side here. Cos theta is 0.4 over 0.5. So simplified it to 4 over 5. Okay, so we have TA times 4 over 5 plus TB times 4 over 5 equal to 0.3, radius 0.4, omega 8 square. Okay, then let's say we divide by 4 over 5 to avoid fractions. Okay, then we get TA plus TB. Okay, this whole thing divided by 4 over 5, so we get 9.6. So this is equation 2. Okay, so with equation 1 and 2, it is going to be simultaneous equation. So let's say I substitute 1 into 2. Okay, substitute 1 into 2, then I will have TB plus 5 equal to TB plus 5 plus TB again equal to 9.6. Then I will get my TB. TB equal to 2.3 Newton. Okay, so that is the first part of the answer, which is the tension in the string BP. Yeah, so we get it already. Now we need to find the natural length of this string. So as we know, that string is elastic. Is an elastic string. So we can use the formula TB equal to lambda x over L. So the TB is 2.3, lambda is 46. The extension we actually don't know. As you can see, let's see the question again. We don't know the natural length. We just know that after extension it is 0.5. After extension is 0.5. Okay, so we just set up unknown then. So after extension it is 0.5, and let's say let the natural length as L lah, let's say. So after extension is 0.5, then you minus the natural length, then you get the x already, the extension. So the bottom we put L also, the natural length. So we just need to solve this equation and find the L. Okay, so 2.3 L equal to, multiply inside, 23 minus 46 L, then 48.3 L equal to 23. So L equal to 0.476 meter. Okay, so center. Okay, a particle P of mass 0.3 kg is attached to one end of a light elastic string of natural length 0.8 meter and modulus of elasticity 6 Newton. The other end of the string is attached to a fixed point O. The string is projected vertically downward from O with initial speed 2 meter per second. So if we look at this information, let's try to imagine. So let's say we have a ceiling here. Okay, so point O is here. Point O. The string is attached to the particle, and the particle P is released from rest at the point 0.4 meter is released from rest at the point 0.4 meter vertically below O. Vertically below O. So, okay. Now let's draw out the picture first. Okay, so this one. Okay, 0.4 meter. But as you can see, the natural length of the string is 0.6. So you should expect initially it is not taut. Okay, the string is bent. It's not stretched or it's not straight. So it's bent like this. As the string has a natural length of 0.6 meter. 0.6 meter. Okay. Now it's released from rest. So that means initially it has no kinetic energy. Okay, initially it has no kinetic energy. So we want to find the greatest speeds of P. Okay, so greatest speeds of P. So imagine what happened here is you release the particle will just go down. So when it goes down, there is a decrease. There is a decrease of GPE. Decrease of GPE. So when it goes down, the kinetic energy should increase also, as it's getting faster and faster due to the gravity. And then after that, it should have increase in elastic potential energy also, as the string is stretched afterwards. Okay, so now we have to consider greater speed also. Greater speed. So in what situation it has greater speed? So likewise, greater speed means maximum V. Maximum V means dv dt equal to 0. That means A equal to 0. Acceleration equal to 0. So based on Newton's second law, resultant force equal to ma. So if A is equal to 0, resultant force should equal to 0 also. Okay, so there is no resultant force. So what kind of forces that act over here is it's not at the beginning. At the beginning, of course, that is not the maximum speed yet. Okay, it's not the maximum speed yet. It's just released from rest. Okay, it is not moving yet, so we don't have maximum speed at that time. So the moment when it's have maximum speed, right, it should have go down for a particular moment, and at that time the string is stretched, and then they will have tension ready, and then the weight is acting downwards. The weight of the particle is acting downwards, and no resultant force means the T and the W are equal in magnitude. So Fr equal to T minus W, right? So no resultant force means F0 equal to T minus W, and hence T equal to W. T equal to W. So tension, since they give modulus of elasticity 24 Newton, so we use lambda x over L equal to W. W is mg. Now we substitute value. So 24, extension don't know, natural length 0.6, m is 0.3, g is 10. So we can get the x 0.075. Okay. So after that, we get the extension already. This is the moment when greatest speed happen. Okay, it happens when the extension is 0.075. And now let's work out the energy equations here. So GPE is equal to mgh. So the m is 0.3, the g is 10. Okay, the h is the one that we need to think about. Okay, so the moment when it has greater speed, it has been extended by 0.075. So meaning that from here to here, it is actually natural length plus extension, which is 0.675. And so that is the length of the string when it has greater speed. And if you compare with the 0.4 meter, that is the initially distance from the ceiling. So meaning that the change of height here is the change of height is the h, the change of height. So let's put the working here, 0.675 minus 0.4. This is the change of height. That is the change of GPE, which resulting in the change of GPE. So we put it in that way. And then kinetic energy. So initially it is 0, and finally it is, let's say, V. 1 over 2, 0.3, then V square. Initially 1 over 2, 0.3, and 0 square. Initially it is at rest. And then there is elastic potential energy also, which is lambda x over lambda x square over 2L. Lambda x square over 2L, elastic potential energy. So lambda is 24, x square 0.075 over 2L, natural length 0.6. Okay, so we need to work out this equation, and then we have to find out the V. Okay, so the working, I leave it to you. So at the end, you have to get 2.18 meter per second. So that is the greatest speed. Okay, so after that, we have part 2 then. Let's look at the next page. Okay, part 2. Calculate the greatest distance of P below O. Okay, so in order to count the greatest distance, so let's think about what concept should we use first. So the greatest distance below O, right? First of all, we have to think of this is maximum displacement. Maximum displacement is like maximum S. So we have to do the SDT equal to 0. ds dt equal to 0. ds dt equal to 0 means v is equal to 0. V is equal to 0. So it means what? It means the particle keep going down until the string extended more and more, and then at the end it stops. Okay, it stops. So let's think about the change of energy at the same time. Okay, the change of energy. So as you can see, the particle keep going down. So we should expect the particles have increase in EPE. Okay, increase in EPE. That's one thing. And then as the particle keep going down also, so we should expect the particle have increase in GPE also. Increase in GPE. Increase in GPE. And after that, because the particles stop at the end, the moment when it reach greater speed, so there should have, so depends on where you consider. If you consider the starting point and the end point, so that initially is at rest, so at the end is still at rest. So if you consider the starting and the end, there is no change in kinetic energy, because initially is at rest. When they reach greatest distance, it is at rest also. So if we consider that 2 points, there will have no change in kinetic energy. So if that is the case, let us ignore the kinetic energy then. Okay, so we just care about the two energy here, the GPE. The GPE should decrease, because the particle go down. Is going down, so the GPE should decrease, but the EPE is increasing. Okay, so now the EPE, right? EPE, okay, EPE is lambda x squared over 2L. The GPE is mgh. Okay, so let's substitute the value. 24 multiply with the extension. We don't know the extension, so we need to find out. So let's say I call it x. Okay, so we call it x. It's a new extension actually. So 2 times L 0.6 equal to mgh 0.3 times 10 times the height. Okay, so the height here, let's think about it. The height here is the change in the height. Okay, so the change in the height, which is, we have one unknown there. Okay, so okay, so as you can see, the string is initially the ceiling is here. Initially the string is 0.4 meter. So after that it is straight. At that time it is 0.6 meter. Then after that there is an extension, don't know how many meter. So the extension is x. We are finding for that x now. So the change in height is actually from this level to this level. Okay, so which is 0.2. As we get 0.2 by using 0.6 minus 0.4 to get the 0.2. 0.2 is here. Okay, let me draw. 0.2 is here to here, and then here to here is x. Okay, so then altogether 0.2 plus x. That is the total change in height. Okay, so we put it here. So this is 0.2 plus x, and we need to solve the question to find x. And let's say, okay, so we do this, we will get 24x squared over 1.2. 24 over 1.2, 20x squared. So we get a quadratic actually, minus 3x, 3 times 0.6 minus 0.6 equal to 0. Okay, then we press calculator to solve the quadratic equation. So we will get 20 minus 3 minus 0.6. Okay, so we will get x equal to 0.264. The other value is a negative value where we can ignore. So this is invalid. Okay, so we take 0.264 as the extension. Now, what they ask is the greatest distance of P from O. So if you see the picture here, this last picture, right? If you take it from O, right, you have to add another 0.6 to it, the natural length together with the extension. So we get the greatest distance here. So the greatest distance is 0.6 plus 0.264, which is 0.864 meter.